So the motivation of the goal for the next 45 minutes, I think it's 45, right, Brian? Yeah. Is to talk a little bit about science fiction. And we picked the title of Exascale, more or less, for the discussion. Addison and myself did a panel, something similar like that. It was in
Stanford.
In Stanford. And Addison had a lot of things to say, so we decided that this time he's going to sit on the table.
So I'm all done, right?
Yeah. So I prepared a few questions that I wanted to ask the panel members, but definitely is to go to have you bring topics as well. Doesn't mean that you need to ask questions. You can also raise your opinion. And as more you argue with the panel members, I think it's going to be more entertainment. So please do. So I'm going to start with the first question. I think Addison knows about what's the first question. We did it last time because I think there is some discussion that needs to be done around that. And so the first question is, what is Exascale? Or how you define Exascale? And
did you want me to go on my rant, Gilad?
Yeah.
Hopefully I won't rant too much, but it's just a discussion that I've been starting at a few different conferences before, just because it was bothering me that we've invented this portmanteau word, exascale, which is fun, but I was wondering what the difference is between exascale and exaflop. And I think what we mean when we say exascale is that we're making a nod toward the fact that in order to have a productive exaflop, you really need to look at all of the different elements of system scalability, whether you're talking about software, facilities management, memory, power. There are any number of issues that are all part of the discussion, but from a practical standpoint, when we say exascale, I think we all really mean exaflop, by which I mean, I think once someone produces an exaflop system, we'll say, congratulations, Exascale has arrived. But if it's not capable of an exaflop, I have a hard time of envisioning someone saying that it's an exascale system. So if an exaflop equals exascale and exascale equals exaflop, then really they're synonyms. But we're talking about exascale in order to make us feel better about the fact that we're trying to consider all of these different elements in scalability, which is appropriate, but I was just noticing the shift in terminology and as an analyst trying to get to the bottom of what we actually mean. Did you want me to ask a question or pass it off to somebody else somehow?
Any other views on
what does an exascale mean to the panel, right? What does exascale mean to you?
I mean, the word itself is a very simple definition.
Well, what is it? If it's a simple definition, then give it to me, right?
So it depends on if you're talking about peak performance or sustained performance.
It's a simple definition. It depends.
So, no, it really is. I mean, you've got to have a milestone, something to shoot at, a target to shoot at, right, especially for funding agencies. And so you have to call it something and have to build something around it.
I guess the working definition for most of us will be an exaflop of delivered impact performance, right? Now, that's obviously not useful. Yeah. But that's what the definition will be, because that's what will get it in the top 500. I know in SKA terms, it has no meaning, an exaflop of impact. So in the SKA, it's an exaflop of delivered application performance. Okay, so those FFTs and those gridding algorithms all need to deliver an exaflop of sustained application performance. Then that's how we define it within the SKA. It's on delivered performance of the application. And I think in the real world that really should be what it's about. Unless you have an application that can be delivering the performance, it's just a top 500 number, which has less meaning.
Which mean that exaflop will come before exascale.
So those numbers that I was presenting in my slides were not an exaflop of LIMPAC, it was an exaflop of application performance. So the LIMPAC number would have to be much higher because we're not going to have 100% efficiency of the code. Okay.
Yeah. Yeah, so that's what I said. First we're going to see exaflops, and then we're going to see exascale.
Well, I think that's the point, right? When we say exascale, I think what most people mean is a productive exaflop to me, but that's a variable kind of measurement. And therefore, once we have an exaflop on LinPack, someone will say, well, that's exascale, it's meaningful to me, but I think a lot of other people will say it's not meaningful to me yet.
Because, this just sidesteps all the difficult issues, doesn't it? Because an exaflop of LinPack, we can conceive of that. But can you conceive of how do you actually deal with and derive knowledge from an exaflop application's worth of data? If you're really running an application at an exaflop, and you've got some poor postdoc that's got to squeeze an exaflop's worth of data through his brain to work out what's going on with that application. So deriving data from the knowledge at Exascale was a much bigger problem, because then your postdoc has shitloads of data to deal with. And how does he analyze that, and how does he derive knowledge from Exascale systems in scientific workflow? This is a much bigger problem than just running LinPack and getting a good number. And this is where we should be concentrating on, is how we build the back-end data storage and data analytics and workflow processes to deal with that much data. It's much harder.
Okay. Any question from the audience? Before we move to the second one. Going once, twice. Sold. Okay. Second question with, I think, Addison also probably is expecting. So we tried to say what Exascale is. Now the question is, what are the gaps that we need to address in order to get into exaflop, Exascale in 6-7 years, more or less from now?
Yep. Well, so I'll go back to the it depends argument. If what we're talking about is the first exaflop LinPack top 500, I would say that the largest barrier is probably power consumption. Although there are a number of barriers, that's probably the one that's the biggest to me. I think it'll come in Japan first. I think it'll probably be a very power-hungry system. It wouldn't surprise me if that system in 2019 was on the order of 100 megawatts. But Japan would be capable of that, and I think it's a strong possibility by the end of the decade. Now, if you mean it's got to be productive exaflop for me, and I've got to be running real applications at Exascale, then I think for most of the industry, the number one barrier becomes software. You could stand up that many flops. How do I get an application to take advantage of that many components and run efficiently at that scale? Software trumps everything else by a lot. And as for when it would be, well, it depends on entirely what the application is. Once we have an exaflop up, you'll get a few applications, probably in bio and life sciences first, that would start because they're more parallel. They can start saying, hey, yeah, we're going to take a run at that. But by industry, it'll take longer and longer depending on what your application is.
Yeah. Rich?
I would tend to agree with that. Being able to afford to run the machine is probably number one. And then
so that's funding. So the gap is funding.
It's funding to pay for power, and then well, of course, no one wants to run 100 megawatts if they don't have to. So then all the challenges of technology come that folks are paying for to try and improve that. But I totally agree. The number one problem is how do you extract enough parallelism out of applications to be able to actually use the compute power, unless you're doing some sort of ensemble average or the like. It's a little easier to do that.
Paul, do you want to give your view?
Yeah, again, the guys have summed it up really. Power and parallelism are the two inhibitors, and really, if there's a desire for it, if there's a benefit, someone will do it, right? But if it's just a trophy machine, if it's just a trophy machine with no real benefit, then I think it will be unlikely. But if there is a need for it, for a particular application, then it will crop up. And this is again where the SKA comes from. There is an application that needs it, and the desire is there, so it will be built. But again, all the risk and the complexity is much more in the software than in the hardware. So when we're looking at the risk register and you're looking at where the complexity is and most of the budget's going to go on the SKA, it's not the hardware, it's the software.
And I assume that Professor Panda is going to agree with the software part.
Yes. Yeah, I think the software matters, and I think all the issues, whatever got discussed, like power, everything matters. But I think as we have seen in the past, so I see the way these machines will be coming, first with more power. I mean, there will be some deployment of an Exascale system with high power. Then gradually some applications will come up, demonstrate. It could be even starting with HPL or the new HPCAC, or some of these benchmarks will come, then bioscience applications, and then gradually people will try to cut down on the power, and more applications will come. So I think it'll happen in phases. That's what I think.
Yeah, I appreciated your presentation very much. The discussion of parallelism here, the evolution of MPI, and that programming model, MV8 pitch and the like, are really critical to the discussion here, because we're looking at not only the greater scalability, but the evolution in the processor paradigm that's going to carry us to that next level of scale, with a lot of different options in play right now. And I assume that's something we'll continue to discuss throughout the panel, so I won't broach the full topic quite yet.
No, you can, but that's fine. We can tackle it in the next few questions. Any comment from the audience?
Well, I had a question for Paul. Will you guys submit? Will you run LibPAC?
No.
Absolutely not.
No.
So might you be the first to be doing Exascale work, but there won't be anything to check mark it off because there won't be a top 500 entry?
Probably, yeah.
And you're funded, whereas Exascale really isn't today, at least from the U.S. government.
Well, yeah, we're funded up to phase 1, which is not an Exascale, but yeah, we expect to be funded on phase 2, yeah.
I would bet Paul would be among the first, but behind the scenes, I would bet that the first non-public Exascale infrastructure would be at Google.
We're not going to be designing, extreme parallelism into the infrastructure. So our impact across the whole thing will probably not be sensible, because that would push the design into a non-necessary direction.
There has been a podcast on HPC Wire in February about a guy named John Fitzpatrick, and he claims he wanted to build an Exascale computer this year already. He has founded a company called Exascale Power Company, and he wanted to build it in Oregon somewhere. He shifted it to Oklahoma, but there's only very, very little information about it. Can anyone of you comment about this? Do you know about this? How serious this is?
I don't have any information about it.
Yeah, I'm surprised it's still on HPC Wire.
I guess it's using pixie dust or something.
So, I have one question. You said earlier that we need to find the applications that will need or benefit from Exascale. I think that there are several, like life science, as was said, or weather forecast. The question is, will the government be ready to pay for that? Otherwise, we need to find some business cases for Exascale. Like a company would be willing to invest on hardware, software, and everything to make that happen. Do we have any idea that there are some companies beyond Google who might be doing HPC in the town or something like that?
Someone else answer first. I need my laptop.
Yeah, I guess it's hard at the moment to envisage, a real driver because the applications are not ready. And even life sciences at an exascale, you're going to have to be wanting to sequence a lot of genomes to use an exascale.
And I would say that there will be more and more cases. We live in a world where we collect more and more data. And there's more and more things you can do with data, not just scientific simulations and things of that sort. But you can look on the future of healthcare, for example, where you can analyze millions of cases, and probably you can understand what's going to happen to you in the future before you even getting sick and try to start to treat yourself. So I think there's more and more applications that are going to be involved, which relies on the data that we collect, and Paul talks about SQL. Yeah, it's another example where...
But these machines are subtly different, okay? So now we're talking about, a typical HPC simulation guy thinks of an exaflop of one large scalable system running one large scalable application. This world is not like that. This is a data throughput world. It's not one big parallel job. It's many, and it's data, and it's streaming. So these architectures are different. I would not design that architecture for a Limpact machine. And so the funding we're getting from STFC next year for Dirac-3 is a data processing system, so we're getting around £8 million for that system. And I'm not designing that to be a Limpact killer, because lots of my investment are going on non-Limpact necessary items, and that's because it's data streaming and it's data processing, and those systems are different than Limpact killers. I think Limpact killing machines are just not interesting anymore.
So what you're saying is that we are evolving from data scale HPC Limpact type simulation to big data Exascale is something where the wealth is actually in the data and not in the results.
Yeah, if you want to take a polarized view, yes, obviously the world is balanced, but I think there needs to be more emphasis on the data processing side and less emphasis on the Limpact killing side. Up to now, the industry has been focused on Limpact killing, and now all my efforts and all the efforts in the design we're working on are on the data side, and then we'll end up with a more balanced systems that are focusing on data throughput and data processing, as well as computation. Obviously, there's a large need for computation, but that needs to be tensioned against a larger need for data processing and data analytics and deriving knowledge from it and visualizing the data and that side of things. And that's where the smart money will be. Limpact killers are easy, it's just a function of money. And bright guys like this doing the parallelism. Right? There's a space for that. But I'm more focusing on data.
I'm going to say your question was specifically if government is not spending. I mean, government tends to spend on what does big science. I mean, the sort of problems that governments tend to address are things like, your large-scale physics simulations and the like, which are very, and which, in industry they don't do as much of.
I'm sorry, I had to stand up and get my laptop. The reason I did, you were talking about applications for Exascale. Intersect 360 Research has been working on a study that we're about to have a draft out of. I wish we had had it prior to this conference, but it's with the United States Council on Competitiveness, specifically assessing the impact on industry of government investment in Exascale. Now, with apologies, this is a U.S.-focused study. I think a lot of the inferences or insights would be applicable to multiple geographies, or really any geography. But with regards to your question about applications in industry for Exascale, in the survey, industry respondents were optimistic about the ability to use up to 1,000-fold increases in performance and actually utilize that within the next 5 years if it were affordable or offered to them. A few statistics, 68% of respondents, these are all industry respondents, felt they could use a 10x increase in performance over the next 5 years. It goes to 57% say they could use 100x improvement. 37%, more than a third, still agreed when the threshold is increased to 1,000x. Now, software is by far seen as the most significant limiting factor in achieving the first 10x of that. It trumps everything. If you go out to 1,000x, software limitations are still up there as like the second greatest barrier, but it comes in behind the cost of the hardware itself to get out to 1000x, which also maybe isn't surprising. Now, really what you get into is how much do they rely on government investment in terms of driving that, and I've got any number of statistics that suggest that industry really looks to government to set the pace in investment in new levels of scalability and supercomputing, and then they hope to migrate those technologies into their own organizations. 62% of respondents agreed with the statement past government investments in new generations of supercomputing have had a benefit on my company or industry. Only 4% disagreed with that statement. There are a number of other statistics I won't get into, but when you get into the qualitative interviews with industry members about, how's that working now, generally companies will talk about, it's a good thing, but that technology transfer from government to industry needs to be improved in the U.S. specifically here, but I think elsewhere it would come up as well. And that's another major indicator or key finding from the study. So I'll stop rambling there. I just wanted some of the stats in front of me for my answer.
Just one observation on that. I think there are some odd statements in there. So if a majority of people think that software is a problem to get 10x, but then to get 1000x, the software problem goes away. Actually, it's much worse.
No, I didn't say it goes away. The cost of hardware, comes up and is actually a more significant problem.
That's because they don't understand that the software costs are not linear. It will ramp up. In fact, it just can't be done. It's not even a function of money anymore. Hardware is just a function of money to get the performance of software. It just can't be done. And so the software problem actually becomes much bigger the larger you want to go. No, they just don't comprehend it.
So does the cost of hardware, though.
Yeah, but it's linear, right? And you can just get it. A function of money, the industry will give it to you. Intel will fall over themselves to give you the hardware for the right money. But the software, the ISVs just haven't got a clue. And the industrial users just are insulated from that because it's not their software. And so the software costs get much worse, and it's just not possible. So I find that respondent survey, I think, paints a false impression.
What I'm talking about here is you're rating barriers on a scale of 1 to 5. So we're counting just roughly what percent of respondents give something a 4 or a 5 on how significant is the barriers. And if you look at achieving the next 10x, then scalability of software, 51% give it a 4 or a 5, which is also the highest average on the scale of 1 to 5, and it's the number 1. If you go out to 1000x, the scalability of software goes up to 64%, and it's the second highest weighted average at 4.0. So those all go up, but people also consider the cost of hardware, and that increases faster just in people's perception of the barrier in terms of how to get to the next 1000x. But I absolutely take your point. In practicality, scaling software 1000x is very difficult, and it's not linear from 10x. I'm just giving you the survey responses.
It's just interesting to see how people have a lack of understanding.
It's quite a question of this 10x or 1000x. I mean, people love to have more computing power, but do they just want 10 times more? I guess when you ask the question, do you just want 10 times more throughput, or do you want to be able to run at 10 times better resolution, which might involve like reprogramming from MPI to CUDA or something like that, and maybe my weather model doesn't program into one of these other architectures very well or at all.
Earlier questions in the survey about 10x, 1000x, just stated 10x, 100x, 1000x improvement in application performance. The specific question you're asking about in terms of rating the barriers, the exact text of the question was, to what extent are each of the following limiting factors to achieving 10x more scalability or 1000x more scalability? I suppose there's room for the survey respondent to have implied the word scalability in different ways.
But the way it's at, it does sound like 10 times say more resolution. It's not just more throughput. It's a really a more complex.
The intent of the survey was to talk about application scalability there. it's a web-based survey. It's hard to get all the way into the head of everybody who's answering it.
People generally want their cake and eat it, don't they? They want more resolution, and they want it faster, and they want it cheaper. They want everything higher resolution and cheaper and more throughput, more slots. Industry tend to think in time much more than researchers would in academia. The turnaround time for a job, a quicker product. Industry people tend to think a lot more about time to solution.
I'll say, by the way, this full report will be publicly available through the United States Council on Competitiveness. The complete draft is due by the end of June, so I'll be working on it throughout the conference. It'll probably be published in July.
So I have a question. I'm okay with the exaflops on the impact standard if that's what we want to use as a guidance, but we got to get rid of the mixed precision prohibition. Anton uses mixed precision. Nobody does molecular dynamics better than them. In fact, we should get rid of IEEE 754 double precision and ECC because the embedded space is going much faster than the traditional HPC space. I mean, if you want CPU and DSP on the same die, you can get that from TI now. If you want CPU and GPU on the same die, you can get that from NVIDIA now. And they're moving fast because it's 10 times the single precision that you can get off of it than the double precision. So have you guys investigated the embedded space to use in some sort of iterative refinement fashion or mixed precision? I think that's where all the innovation is going to come from in the next 6 years. I mean, you'll be able to, in the 11 nanometer process, you'll be able to tell the vendor, hey, I need RDMA offload, they'll give you that layer. I need TCP offload, they'll give you that layer. There's going to be all sorts of stuff on the same die right now. There won't be any dark silicon. And that's where all the action is going to be held. You can go down to the Adapt Kiva booth and ask them for 10 gigaflops per watt right now.
We will be looking at all those disruptive technologies in SKA because we need to be driving those barriers. So yes, we will be looking at that technology. And anyway, today on our GPU cluster, it's very popular with the molecular modelers for that very reason, right? They're all running single precision molecular modeling on the GPU cluster, and those guys are having a field day. And so, what we're talking about over Nexus Cloud is, a top 500 definition, but a definition is never going to be correct. It's just a definition, it just is what it is. But in the real world, you're completely right. People are looking at this stuff, and it will have many places to sit.
Yeah, and I think these new trends are happening because of these newer big data applications and coming. So it is no longer like the field is not just for HPC or scientific computing. So gradually we're seeing this new generation of applications are coming. They don't need all the floating point performance and all. So we'll see a gradual shift in the hardware, and at the same time newer applications will be able to take advantage of the new machines, and that will have its own cycle. And then both at the hardware level and also in the middleware level, also on the applications level.
Okay. I have a couple of more questions. I'm trying to see if we can get to them before. We have 10 more minutes, right? So another question that I would like to ask the panel is there is increased trend in what you can call open systems or open platforms. For example, what Facebook is doing as part of OCP, creating standard for multiple elements, and I think a week ago they announced they're going to create a platform for switches, Ethernet switches, for example, and opening that, which is people can look at it as a direct attack at Cisco, for example. But going open platforms enable people to do innovations in maybe silicons and a software, but platforms are becoming open. Is that a trend? Is that what we're going to see dramatically taking HPC as well? Or that's going to be limited to the Facebooks of the world?
It's a trend I hope will continue. It started with the advent of clusters when they commoditized, and this is just a further commoditization process. I think it's unstoppable, and the price point will drive it. And so again, in a lot of my personal investigations in SKA, we're looking at just that type of platform, okay, of that scale-out compute data center infrastructure that Facebook may have. Okay, so I think there's a lot of benefit in that model, and it could well catch on.
Yeah, means the open standard always has a lot of benefits, but more from the end users community. So you see the benefit, but then again, it's from the company's perspective, what is the benefits from their side. So I think we have been in this community for the last decade. I mean, some open source things come and then again get closed, then something new open up. So I think we'll see those kind of patterns continuing.
I think we will see multiple types of open standards, open platform initiatives. To the earlier point about mixed precision or embedded systems, or Paul's earlier comment about data versus compute, the cluster revolution that kind of ushered in terascale roughly in time brought about a wave of commoditization, where prior to that, HPC systems were largely proprietary in different platforms in the RISC era or the Vecta era. And we're now swinging, as we head toward Exascale, back into a more diverse ecosystem, particularly in processor technologies. We commented 2 years ago that we couldn't think of a time when there were more different processor architectures as an active part of the HPC discussion. If you look at x86, accelerated x86, ARMs, GPUs, floating point DSPs, FPGAs, there are still RISC-based systems out there. It's very difficult for the end user community right now in terms of determining what platform they want to be on 5 years from now. We see end users putting a lot of different architectures into trial, not very many different ones into wide-scale deployment yet, but everyone's trying everything, trying to place their bets on where things are going. As such, any of these different arenas, if you will have standards that are evolving. But when you have a lot of standards, what you really have is not a single standard, right? Now, you'll have standards depending on what architecture you're choosing. It's important to realize that this is not a right versus wrong kind of argument. I'm trying to choose the architecture that's right for me. But we could be heading into an area of a lot more I hesitate to use the term proprietary because they're all open in different ways, but more diversity in or less commoditization or standardization in terms of what's going to be the process or architecture that's going to carry us forward. Yeah, I mean, big challenge for the user community, huge. Sorry to interrupt.
No. So, I mean, we're definitely in a stage in terms of technology where there's some huge technology challenges that need to be solved moving forward. And so inherently, when you're trying to innovate and try and figure out how to go around, get over these challenges, you have to have a lot of different approaches until someone figures something out, and then maybe things will stabilize again, and then we can get more into a mode where a lot of people do the same for a while.
We focus on the processor. Do you really think it's more the processor? In my opinion, it's more the memory hierarchy and the low speed at which you can access memory. And in this context, I guess maybe the latest development that HP announced could be a way that opens new possibilities.
The Memristor technology, I mean, yeah, I loved we did a podcast on that a week ago. If you didn't hear it, you can find our This Week in HPC podcast on our website or on InsideHPC. I agree. The memory hierarchy is absolutely critical to the scalability. I tied it into the processor architecture discussion because it seems that each of these different architectural approaches has implications in terms of what the memory system looks like. So it's not just how the flop gets delivered, but absolutely how the data gets delivered from memory or from cache or whatever the architecture looks like, and how data flows through the system. I wish there were more discussion of different interprocessor architectures, different topologies, different networks, different fabrics as part of the overall discussion. The diversity is happening right now at the processor level. I was accused last year of being far too processor-centric. You HPC analysts, all you ever care about is processors. I thought that was dramatically unfair. I defy you to find another analyst who's spent more time studying parallel file systems than I have. You know, the data movement through the system, the data infrastructure is absolutely critical to scalability, but the diversity right now in processors is undeniable. It is an unmistakable trend that is having huge implications. You can't ignore the processors just because you're going to be accused of having a bias.
And I would say, I would agree with you on the process diversity. I think this is a great thing. It's also a great thing that a lot of this is licensed. The companies are now licensing and open in their technology. So if you have diversification of the processor, what we need is diversification and open platforms for the fabric. The fabric really becomes the lock-in that we need to fight against as an industry. Right? If we don't want to get locked into to single vendor solutions, the fabrics that are out, the chip-to-chip fabric on the board, you know, at the interconnect level, that's all open and nice. And since we've had InfiniBand, this has really driven that cluster market. But if we don't want to get snapped back to the proprietary world, the fabrics need to be the focus. We need these guys to be able to plug and play different processors on the fabric that's open. Yeah, and that's the real area that as an industry we need to look at, is that fabric.
I loved the HP announcements from a week ago, the Memristor, also the photonics that were part of the machine. Okay, does everything have to be a cloud? That's kind of what bugs me about it. But down at the individual technology level, the Memristor stuff, the photonic stuff, I did comment that I wish there was some fabric or topology or architecture discussion as part of that. And, you know, I'm waiting to see how they're going to put all those things together.
Because then this, you know, the comment over there about the DSPs, it comes true. You know, we are moving into a heterogeneous world.
Sure.
And for this to work, the fabric needs to be the center of the discussion.
Well, it's not the center of the discussion right now, I'll tell you that. It is the gaping hole in the discussion right now.
Exactly. And I think we need a focus on the fabric. Otherwise, all the joy we could get from this diversity will be lost because we can't utilize it.
Yeah, how the data moves across the machine is going to be a critical part of the discussion, and one I'm looking forward to spending more time on.
Okay, another question. I have two last questions, see if we can fit them in time. So, you know, in the past years, x86 was the dominant solution, right? No doubt. It still is.
Still is.
But recently we're seeing movements. So IBM created Open Power, which is backed by Google and other companies, and they start to drive power as an open power solution. In this conference, we're probably going to see the first demonstrations of a 64-bit ARM platform as well. So are we heading into serious competitions to x86 or not? And Jeff, if you want to comment, you're more than welcome as well on this subject.
I have statistics on it, so I can start. Since the beginning of 2012, 44% of HPC systems that have been installed have had accelerators as part of them, whether that's Xeon Phi or NVIDIA. So that's still x86 based at the core, but it's accelerated x86, which ought to count as a different model right there, especially with respect to 90% of those being NVIDIA GPU, which is moving a lot of the computation off of an x86 platform and onto the GPU in particular. Now, NVIDIA is also quite likely going to embrace ARM plus GPU in a very strong way. We haven't seen any kind of reasonable volume of ARM adoption thus far. There have been some notable experimentation, most notably from Barcelona, Also, I think
But
Sandia.
it was on a 32 bits, not on a 64.
Right, correct, because ARM64 hasn't been there yet.
Right.
So now that it's out, I'm certain that we'll see some experimentation with ARM. Now, I said that 44% have accelerators installed. People are still trying accelerators more than they are deploying them in volume for the majority of their workloads. There are some noteworthy exceptions. All of this diversity means the short answer to your question is yes, there will be a significant challenge to x86 dominance. It's not there yet. It's, it's going to be a challenge for Intel to hold on to their significant hold on the marketplace.
Okay. Jeff, did you want to say anything about it, or?
There may be a lot of diversity in potential processors, but that chart still speaks volumes that 85-90% of the top 500 systems are x86 based, and if we think thinking out then to the next generation of Xeon 5, that's self-booting as Intel's publicly announced. That's pretty much like an x86 system anyhow. So it's going to take something to crack the dominance.
Not only that, I'll go so far as to say Intel gained significant share in 2012, and that'll be part of my market share or market model presentation this afternoon.
Okay. So I had one more question, but I think we ran out of time. So the last question, just to put it out, is that was a question about what's the future of storage. But I think Torborn is going to do his presentation next. So I guess that you're going to give us the answer instead of the panel.
Storage has a future.
Yeah. So I want to thank the panel, DK Panda, Addison, Rich, and Paul. Thank you very much.
Thanks.